I worked for a few years to create the new geological maps of Apollo landing site, and you could say more or less I updated the geological map, and I will also introduce why I did that. So far, everybody knows the importance of creating these geological maps and how we use different data to gain physical and chemical composition or information from different data to recognize the geological processes occurring throughout the planetary surface. And here, what you can see here are geological maps that were produced in a pre-Apollo era. So these maps were produced to identify the stratigraphy of Moon, but these were also maps that were used to plan those missions. But now, after Apollo era, after Apollo missions, we gain a lot of other information. We got samples, we have more data, and now we have more information about these geological units. But we also have more questions about these geological units. So when we use this information, or the information we have so far, we use the new data, as you have seen in the last hours. That's how you use high resolution data, spectral data, and these spectral data are based on, or they are calibrated with sample data. So we have this information, and now we can update the geological maps and make more accurate geological maps. But for this purpose, we also need updated standards for creating these geological maps. And the reason I created these geological maps was because I wanted to test the accuracy of lunar crating chronology, which I will talk about a bit in the end. So here, what we are seeing is the geological map around Taros Littrow Valley. Here is the Taros Littrow Valley. This green triangle is a position where Apollo 17 landing site is present, and these are old LSE maps. These are the maps you have seen from Mosaic, and you could see that we have a lot of information already there, but we have a lack of standards. We have also, like, there was no fixed standards were set for units, or also not only that, but you can see that one map interpretation is totally different from other. This orange unit, which is considered to be probably Imbrium or Nectarian age, is interpreted in other map as Rathassinian, that is much younger than this one. However, because these maps was required to plan missions, there were slight improvement in these maps. Here is again Taros Littrow Valley. This dark mantle deposit, this orange one is dark mantle deposit, and this lighter one is light mantle deposit, which is kind of a landslide probably due to Tycho crater. But anyway, we have these two main important deposits where the samples were collected from. So anyway, we have this new updated geological map but the thing is that now this dark mantle deposit was apparent to be very young and interpreted to be at Copernican age. So it was not fixed interpretation what is the nature of these deposits. But also we have to say that it was one of the reasons for such a problem was limited data set. They have a lot of photo data, and they could interpret more or less a albedo contrast, but there was very limited data. So this is what we have now. This is the geological map what we prepared. And now we have different interpretations of things because we have this information already gained. We have samples from this deposit, which are dated, and we know that this deposited Imbrium age. We also know what is the nature of the light mantle deposit, and we also can perform better crater size frequency distribution measurements, CSFD measurements, which can give us ages of other craters, which were, for example, certain craters that were considered to be very young are not really young, and we can identify through CSFT measurement methods. And similarly, we can use spectral data to identify more units and with a betterly defined boundaries. So this geological map, it's actually one of my favorite geological map because it is very detailed. It is really the one of the geological map that was used to plan this the Apollo 17 mission. And some of the Apollo data was a higher resolution because the data that was obtained from Apollo orbiters, they had a good resolution, and this map was made on such a image which has a good resolution. However, it's still the same problem. The interpretation of the units are very restricted to image data. So we have, it's again that the age of this purple deposit, which is a dark mantle deposit, was not known. And another thing that was interpreted differently was it was considered there are some, these are the highland areas, and it was interpreted there are some kind of vents that are erupting these volcanics there, these red deposits as the volcanics there. And of course, the most prominent features, light mantle deposits, landslide, and scarps, they were all interpreted before. But also ages and stratigraphic was unclear. So this was made by Lokita in 1972, and they updated the interpretation in 2018 after they add all the information they gained from sample studies and other studies. But still, the problem is that this map is dependent on probably single image. This is our new geological map of Taros Littoral Valley, and here we again use different data sets. We don't use one single image. We use images with different incidence angles. We use spectral data, and we use also different methods like CSFT measurements to confirm the ages of certain units. And here we see that the deposit that I explained before was considered the volcanic deposit, maybe occurring from the vents in highlands. In our different image data, we didn't see any evidence of volcanic vents. But what we see in the spectral data, this material that was lying on a highlands, it's very similar to the one that is filling valleys, which means this pyroclastic deposit was, when it was deposited in a valley, the cloud was also covering some areas around the valley. And this is what they couldn't see clearly when in a single image data. And again, then we have, as I say, we have a data from different incidence angle. So we can see that how this light mantle deposit, which was interpreted to be a single unit, we can see several units of this deposit. And for confirmation, we also did CSFT measurements and recognize that they are varying. And yeah, there are so many other details that you could interpret differently. We could see some regolith mixing and mixing around the central cluster. We could see a boulder fields, and you have already practiced how much better you can identify all these features. And now when we talk about better data, high resolution data, we also trace back the traverse or EVAs that astronauts took. So this plus sign is the one where lunar module is present, and this dotted line is a traverse that astronaut took to collected samples. And when we compare with the traverse practice you have just done, you can see how safely these traverse were taken, they were taken on a low elevated planar areas, where this is DTM, which shows a height information, and this is a slope information. So everything blue is below 5 degree, and everything red is above 30 degree. And here we can see that the traverse was continuously at the slopes of 5 degree. Even when they have to choose a path which were a bit higher, they decided to take a traverse which doesn't have higher slopes. So in short, here is a presentation of Apollo 17 maps we created, but here I also described that which are the example units, how we identify highlands on base of the different morphology. We use DTM data to find the extent of structural features like ravines and wrinkle ridges. We use albedo to map different albedo units or units on the base of albedo contrasts. And these different crater classes, we have already talked about how can we use these different crater classes to identify nectarian craters apart from Imbrium craters. And these black hollow craters that we also noticed on the Copernican ejecta in the last exercise, and then chains of the secondary craters. So we use the same principle and finished the geological maps of all 6 Apollo landing sites. And we also made a detailed geological map. Some of these maps are published and some of them are soon to be published, but we presented it already several times. So the reason why we created this map was to test the, as I said, to test the accuracy of lunar chronology function. And Caroline talked about this function in her lecture, but here, just for revision, this function is actually a tool that we use to find the ages of geological units that are not sampled. So all the geological units on Mars or Venus, where you use this crating chronology in a modified form to find the ages of the surface units of these bodies. And how does it work? Again, in very general sense, I would say this n value is what is describing crater spatial density of certain geological unit, and x-axis is based on radiometric ages of samples. That's why, because we have samples just from Apollo and Luna landing missions so far, this chronology function was based on Apollo and Luna landing sites. And to check the accuracy of this function, we have to go back to the sites and reinvestigate everything, including the geology of this landing site. So that's why we created this detailed geological maps. And now I will describe how does it work with this, how we start from geological maps to lunar crating chronology. So here here's a geological map of Apollo 12 landing site. This green triangle is showing this landing site. And we need a uniform geological area to update this n number, this n values, or test this n value for crating chronology. And this uniform geological unit is present on this Mare, this Eratosthenian Mare unit, this green one. And we need to test the crater density on this one. So we updated this geological map from previous geological maps, and then we test how the previous n values were taken. And this blue area is the one that is showing the area which was used to measure CSFTs for testing or creating this chronology. And we notice it's not geologically uniform. It's not having a single geological unit, but there are several geological units in this area. So we, for our geological map, we selected two areas, like a black one for Eratosthenian Mare units and red one for Imbrium Mare units. And we see that we have to take this area on a Copernican ray material here because landing site is present in this region. When we test our N value, that is roughly describing crater spatial density of certain units, we see that this black area that is at the landing site give us two N values. One is younger one, which is giving a relative age for Copernican crater, and then this other one is giving us relative age for this Eratosthenian unit. And we also see that the one area that we select, the black one here, which is ray free, is not giving us the second value, but just a similar value and value like other green unit. And this red value is coming from these three areas on Imbrium H unit, and they are so close together that we can have a one single N value for representing this Imbrium H Mare unit. And again, these N values are representing crater density of, are roughly representing crater density of this unit, which shows this amount of the craters formed at certain age. And when we notice this blue area, it is giving us totally different N value, which was probably a reason that we need to fine tune these values with new geological maps. And this was not the only thing we did, like not just measured finding these N values and creating geological maps. We also investigate where are these samples, representative samples were collected from, and what was the nature of these samples. So we also look for what kind of Mare units were there, and if these Mare units are close to what our mapping unit is, where the landing site is present. And this is where we, I mentioned it before, that's where we came to know that these Mare units probably apparent as intermittent layers of different composition. So for this purpose, we need to take certain range of ages. So this is the red point, which is updated age for updated point for this chronology function, and this is the black point which was originally used. Here again, this red one is the one for Copernicus crater that we have this value for on a Copernican ray material, and this was the original one. And if we look at this chronology function, you can see how much better it fits on these new calibration points. And these calibration points came from more accurate geological mapping. So well, I would say this was not the only project we did. This is one of the bigger projects that is related to this these maps. We also use these maps for several other projects like ISRU studies for finding a provenance or origin of some samples, and we talk about machine learning. We are also using these maps for trainings, and so there are so many other fields I can talk about, but I shouldn't at the moment. But this is the point that we gain all this knowledge now since Apollo era. We have so much data now we need to update these geological maps, and we need to also create more accurate and new geological maps. And with this amount of data, of course, we can create geological maps on any scale, and in any style we want now. And it's and we are not answering questions with these geological maps. We are also opening more and new questions about the nature and nature of area, and we are also still learning more and more about the processes on these planetary bodies, which are used to update these geological maps, which we will create and also that has been created. So I will stop here now. And I would be happy to take any questions.
And let's see if you have any questions. We have a few minutes available, so if you have any questions to Wajiha, put them in the Q&A, and we can try to address them.
And should I stop sharing my screen for next one, or?
Well, you can leave it on for a few more minutes, so maybe some question will arise. Okay, I see
we have no parallel session. Actually, we can even try to, if there is no question in the next few minutes, we can also move on a bit. Or if Gia wants to share something more.
Yeah, oh, sorry, it moved a bit. But of course, I can talk about the different projects we also finished with these maps. Yeah, but I shouldn't go into more details. But as I say that include to this lunar chronology function, we also have a project which goes other way around, where we need to find out where the samples were collected from. And this is where we are using also this geological maps with spectral data and with certain modeling, which says that it is talk about the distribution of the of this data, and then we correlate all this information to investigate different sources of the sample. And it is goes for also for many open questions about the ages of the certain basins, and also accuracy of stratigraphic system. So these are the geological maps that needs to go that needs to be used for answering more questions. In addition, these are also, like you all already have seen, that how the geological maps are used for traverse planning, for landing planning. And this is another paper from Caroline, where they estimate the size of pyroclastic deposit for ISRU measurements, and of course now we do have good spectral data. We can also do such estimations. Okay, this is another project we have done, in which we, as I said, that we still have many open questions, that with Apollo data, not everything was solved. We still have a lot of questions about, for example, nature of tectonics on Moon. And This is also from Caroline, where she tried to find out the ages of young scarps, and we included the ages. We tried to find out ages of the young units for young Copernican age units, and then we also tried to figure out how they fit the story of the stratigraphic, and how could they be correlated. And this is also how we find out there are different different deposits on a light mantle deposit, unlike how it was previously identified.